Let me set shared screen. So the goal of today's meeting is triple. We need to agree on schedule so that everyone feels happy. We need to review the projects that are going on so that we have a good plan for tomorrow's lab, and we need to continue the academic part for excited state theories. So regarding the schedule, so right now it looks like we need we do have and we do need total 4 lectures more. Okay, so we are in what is left for our lectures is starting here. So we have a little bit different numerations of lectures, but we have left with 4 meetings more this week and next week. So today we will finally get to the time-dependent density functional theory, which is one of the theories for excited states. On Thursday we'll get through flow chart for this theory in the same way as we did for all previous chapters, for optimization, for Hartree-Fock, and for DFT. And then next week we will completely invest time into the projects. So for presentations, I believe that since we are meeting online, the restrictions are not as strict, and I have in mind 2 options that we can make more options, but I would like to check your availability and interest. So I'm going to bring up the screen so that if anyone is with camera, I can interact directly. And I will bring this slide again. So we do have left 4 lectures and 2 labs, and typically we may try to use the 4th remaining lecture for presentations, but I have a fear that it will be too close. And if everyone agrees or no one will protest, I suggest we make presentations on the finals week, so it will be like an analog of exam, but with less stress presenting your projects. There is a standard schedule depending on where we meet during the semester, when should be which time should be our final exam. But and according to the schedule, final for this class should be on the lucky day of 13th of May, on Wednesday evening. But I suggest that too late at evening and too early at the morning is a big stress. And Wednesday evening will be like 2 a.m. in Germany, so it will be very discomfortable for Rebecca. So if anyone asks for my vote, I would select the Thursday May 14th, and we can start regularly as our class is on 11 a.m. And I would like to check your votes on this idea, and then if after collecting your votes, I will make sure that the room is reserved. But if there will be no consensus, I am open to select a date and time that is comfortable for everyone. So let's discuss this aspect early enough. So other, please answer or type in the common chat if the Thursday, May 14th, 11 a.m. sounds acceptable for everyone, or if someone is not comfortable, let also please answer. Amir approves, so one vote is for. I'm also for this, so 2 votes. Yang Chao is also for it. So we have 3 votes, and we need at least, well, I don't know if Raju is okay. It's Mahek, Salim. So we need, who else we need? We need Rebecca. Zhaofan supports. Thank you much. Okay, thank you, Rebecca, for supporting. And let's check if Steven is okay for this time. Steven, please answer or type if. Okay. Then I think it's not a simple majority. It's 100% votes. Let's do it on Thursday, May 14th, and then it will be a lot of, well, it's not a lot, but substantial, noticeable time to finish and have everything prepared. Very good, very good. Thank you for this support, and I think we can go forward without too much of the rush. Okay, and we're moving Wednesday and supporting Thursday. So I'm going to quickly go on over the projects that we are doing, and if anyone is well, we will invest time for projects tomorrow during the lab, but if there are some very quick questions, we can cover today. So here are your votes, and I have a little ambiguity in my head about project of Rebecca. On one hand, she was interested to do flakes. On other, I don't know, her advisor suggested to do voids, big vacancies in graphene. So if one follows and let me give a little disclaimer. The projects are your projects. I can help, but do not feel anything obliged from my side. I will assess only the scientific level and acquaintance with the tools in the course. So subject is not critical for me. So for the flakes, one of the option is graphene flake functionalized by replacement dopant with nitrogen, and then there are orbitals contributed by nitrogen and locally presented in vicinity, and such orbitals enhance absorption and emission at near infrared, and there are additional states in the gap contributed by these dopants that are important to optics. So it's just information you can discuss in private by emails whether this project will be pursued or there will be some modification. So for Stephen was interested in metal organic catalyst where ruthenium is coordinated by 4 bonds to large ligand, and then one by 2 bonds to this composite phosphoxide and nitrogen-containing group, and one bond is empty that can accept either water or oxygen or hydroxyl. And by changing oxidation state, this direct access of water to ruthenium, so there is no steric hindrance from this side, can help water oxidation. So there are several models, and one of them is here. So this one is ruthenium, and one can, the gray clouds are total charge density. One can see that around oxygens and all other atoms, it is takes more spherical form and hybridizing with nearby atoms, and for ruthenium it takes more like square box, because it is a superposition of several d orbitals, and then it takes this spatial anisotropy. And the water molecule is here, but Steven is probably planning to re-optimize it with spin polarization and with different oxidation states, and seeing how stable this water will be connected to ruthenium, and also maybe one of these oxygens from phosphor group will set up a connection. PowerPoint decided that it wants to save. And the next is project by Salim, who was interested in lead halide perovskite quantum dots, which with optical properties facilitated by transition metal doping by manganese 2+. And similar as in Steven's project, the transition metal ions like to be coordinated in the octahedral shape, and the manganese ion in 2+ oxidation state has 5 unpaired d electrons, right? Okay, and in hydrogen atom, d orbitals have the same energy, but in the basic, well, maybe not basic, in the inorganic chemistry course, there is a standard knowledge that if a cation of a metal with 5d orbitals is connected with 6 negative ligands, then these negative ligands act with electrostatic Coulomb interaction onto this d orbitals, and instead of having the same energy, they split. So this x squared minus y squared and dz squared are pushed up, and all others are pushed down. And the splitting, well, it is not our goal because we are not doing theory, we're doing computation, but one can compute this splitting analytically without computer. And if there is a correct computational chemistry theory, it also should be able to predict this thing. So the splitting is important because the perovskite itself is a good emitter, but it has some shortcomings. It's unstable, and it experiences blinking, and when one introduces a doping, it becomes much more stable, and it should emit like pink color, right? And the emission is expected to go thank you transition between these orbitals, and Salim already made some progress, and I with your permission, I'm showing one of your figures. So it is what Salim created. In this model, it is reduced. It's not the whole structure. It's small fragment with 3 leads. Here is lead. Probably there are other leads there, and 1 manganese, and the states inside the gap are superposition of d orbitals of the manganese. You see this 4 petals, like a little flower, right? And they are partially contaminated. They're hybridized with p orbitals on the lead, but there is a hope that in the model that Salim is pursuing, this hybridization contamination by lead is minimal, and it is one of the questions of this research. Also, what Salim is exploring and what is critically important, since manganese has unpaired electrons, it is I spin equals 2 calculation. The research by Mahek was elected to be phospholipid, and I do not. I'm not going to criticize, but I have some constructive suggestions. So I would do this project a little bit differently. So here is the model that Mahek has selected. It is 1 monomer for the phospholipid bilayer. So there is a 1 carbon that sets up branching, forking of 2 chains, which are water repelling. What's the right word? Hydrophobic. And through this phosphoxide group, this part is hydrophilic. In the actual cell membrane, this part is repeated multiple times. So this 2 tails are repeated again and again, and the tails are connected to each other by some mechanism. So Mahek decided to skip the periodic structure with multiple tails and focus on a monomer, and then explore how it will react on the collision, on the chemical reaction with peroxide, which means that one probably needs to draw several peroxide molecules around and then run molecular dynamics. But the positive aspect that if one neglects other phospholipid monomers, the model is rather small and can be computed quickly. This is a big plus, and one can explore elementary chemical reactions in the detail. The negative part is that we are missing the opportunity to describe realistic membrane. So it's just an observation. I'm okay with either way to pursue. Yang Chao decided to pursue the emission by functionalized carbon nanotubes, and to my understanding, he is building using the models with function group adsorbed and desorbed, and it is also shown here and there, and exploring their electronic properties and optical properties, like density of state, spectra. And after those are done, one can go forward and see how this model responds to heating, whether there are some chemical reactions. Amir selected to explore the conjugated polymers. And to my understanding, in project by Amir, there's connection to the multi-scale modeling of mechanical properties of this conjugated chain that is functionalized by alkyl groups. But what can be done in this ab initio computation is, in addition to mechanical properties, one can explore ability of this material to conduct electricity, which is primary goal of this conjugated polymers. And for chemical symmetries, one needs to take two monomers as a unit cell. So the fragment here and there is the same, with only which is flipped by 190 degrees, and the last carbon on the right and first carbon on the left need to be connected. I think Amir is already an expert in this, and he doesn't have this question, but for everyone in the class, let me answer potential question: how this carbon number 61 and carbon number 17 in this molecule can be connected. So if we do periodic boundary conditions, it means we do have primary model and its replica placed nearby. And if we that are in physical, in direct contact, and if you look on their border, then just a second, yes, then the last atom of the original and first atom of the replica have to be connected. And in this drawing, I'm not showing the conjugation, but it is alternating single, double bonds, which are very appropriate for conducting electricity. Jean-Fan is interested to model cellulose, and when we were interacting last time, there was an attempt to borrow structures from databases, X-ray crystallography, but when we want to make sure that what is borrowed from the crystallographic database agrees with common knowledge of what cellulose is, and if it in a good agreement. If not, one can either keep browsing through databases or just build this periodic model in the same way as Amir did and create a periodic structure. The project by Raju is solid electrolyte, which is quite hard for humans to follow. It's a complicated crystal of so-called garnet with many atoms, and if one looks inside, well, it does have several types of metals: zirconium, lanthanum, lithium, and later on the aluminum as a dopant. And the source structure is zirconium oxide. Zirconium likes to have octahedral coordination. By looking into structure, one can identify elements. Zirconium with 6 oxygens connected to it into octahedral fashion. And in between there are additional ions, and after thermal excitation, there are ions that can move across the cell. So let me point out a couple of zirconium. So if you make a slice that just brings up front part and makes everything in the back intransparent. So here is zirconium with which has octahedral. We see only 3 out of them, but other 3 are behind the plane. And to my understanding, the goal of Raju is to explore how the model responds to heating and probably to application of electric field, as well as trying different styles of dopants. So the research procedure that we were already reviewing can be individually modified, but if there are some doubts, the standard thing is to, after selecting model, optimizing geometry, plot density of states, spectra, maybe some orbitals, then heating and run molecular dynamics, and after that, without second optimization, after geometry is perturbed, is changed by the thermal motion, find density of states, spectrum, and some orbitals once again. And then just by comparing these two sets of data, one can make some scientific conclusions. So we will continue going through the projects tomorrow on the lab. I will keep trying my best to answer any questions immediately, as quick as possible. And for the our academic part, let me find where we stopped last time. Yes, please, Roger. Can you please speak closer to the microphone?
I'm running geometric optimization yesterday for almost 11 hours.
How many, Raju, wait, please wait. How many processors and nodes did you use?
Yeah, I used 4 processors and 32 cores.
No. So each, you may look online on the NERSC website for their available resources, but the structure, I think in one node. Wait, yes, let me tell it, and then you continue if your question stays. So one node should have 32 cores. Please double check. They may have updated, and they may have more. And if you request 4 nodes, then you need to simultaneously request 128 cores. And on our account for this NERSC, there are like several million compute hours, so it is very justified. If your model is big, do not hesitate to use like 8 nodes and 256 cores. I think if you do this approach, it will substantially speed up. And when we all will start doing molecular dynamics, this ramping, this increase in the number of nodes and cores will be necessary, because the debug queue is limited to 30 minutes, and this will be insufficient for most of the molecular dynamics tasks. Does it make sense?
Yes.
And I'm sorry for interrupting you. Probably you wanted to ask a different question.
No, I That's what I was going to ask. That how do I know that I need this much code, this much node?
Just play a little bit. If you need more than 8 notes and 256 cores, consult with me. But up to this limit, feel free. So there are resources. And let me bring up.
Because I just asked for 4 nodes and 32 cores.
No. You need to do the simple math and multiplication yourself. So 32 cores per node. If you use more, nodes, you need proportionally multiply the number of cores. Okay?
Yes. Because I thought I wouldn't need that much, but I was wrong.
So just look online for the specification. See, KNL has 68 cores, but if your edit copy, if what you are doing is challenging computational task, you may just browse. This is not a big secret. I'm going to copy it to the common chat. So you just look there for specifications, and the same explanation if you look Control-C. I will bring this to common chat as well. So it is an overview of the facilities, and you probably will immediately become a top expert of most optimal use. And there is a queue policy. Control-C. Oh, just a second. So now everyone has at the common chat the link to this details of the queues and how to use them. So if we run in the debug, it will be almost immediately run, but one cannot submit too many jobs simultaneously. And if you are going to the regular, one can submit like 5,000 jobs and go and drink tea and expect until they are complete. So priority is regular is a little lower priority, but still it will be a good deal. Okay, so you can explore this stuff yourself, and we need to go forward through the academic material. The last time I believe we finished at this slide. So we are looking for response of molecule to external oscillating electric field. In the oversimplified way, electric field facilitates transitions of the electrons from occupied orbitals to unoccupied orbitals. But in all theories that are like solid theories designed for excited states, instead of language of pairs of orbitals, one is looking for ground state and then set of excited states. In a very, very approximate way, excited state is approximately represented by transition between two pairs of orbitals, but there are exceptions. And this orbital picture and excitonic picture very, very approximately can be assessed in the following. So energy of first excited state is approximately energy difference between HOMO and LUMA. And then one goes forward into different excitation energies and going lower unoccupied and higher, lower occupied and higher unoccupied orbitals. And the goal is for today is to assess the equation that generates these frequencies, which correspond to this epsilon 1, 2, 3, 4, 5 energies of excited state, and x, y vectors that correspond to transition density matrix. So the equation here is named after its designer, Dr. Casida, and I had pleasure to see him in person. Well, probably he didn't notice me, but he's a live person, not very old, and he from time to time comes to conferences. So by solving this equation, one can get all information that is needed to assess ability of a molecule to absorb light. Again, same as DFT, this TDDFT, time-dependent density function theory, is not the most precise, but it is balance between numerical precision and numerical cost that makes it most practical. So in order to utilize this equation, we need nothing. We only need to know what is on input and what is output. But in order to support scientific discussions, and if you ever run this equation to defend your results, we need to dig a little deeper. What are these coefficients? We already know what are x and y and what are frequencies, but we need to get into these coefficients. So when we were working with ground state DFT, we had the kinetic energy term, gradient square plus potential acting on the orbital, providing energy and orbital. So the potential that was entering into quantum equation was a first functional derivative, d over d delta rho, of total energy minus kinetic energy. This was equation for orbitals. And here we had the first order functional derivative. Now, instead of orbitals, we are focusing on the density matrix. and density matrix is composed as is related to pairs of orbitals. I, J. So in order to deal with pairs of orbitals, I assume that one would need to take second functional derivative over the total of the energy over the density. So in order to set up eigenstate equation for transition densities, one may form the eigenstate equation that is similar to Schrödinger equation, but the matrix, the super operator that is acting on the density matrix should have elements composed as second derivative of total energy. Let me ask if this idea makes sense, and if anyone wants to object or ask questions in principle for or against this idea. Okay, no one objects, it means everyone accepts, it means it is correct. So if we are looking for orbital, we take first derivative. If we are looking for pairs of orbitals for density, we are looking for second derivative. And here, I apologize for long equations. We are not expected to memorize it, only get some acquaintance. So the elements for matrix A and B in the Casida equation are formed as literally as Coulomb matrix elements for interacting between pairs of orbitals. So if there are two pairs of orbital, one occupied and one unoccupied, there should be attraction between electron and hole. And when we were finishing the subject of Hartree-Fock, we were introducing this notation. So between four orbitals, one can set up this Coulombic terms. And by setting symmetric or anti-symmetric set of indices, it will correspond to different part of this Coulombic interaction. In case electron and hole, electron and hole in pairs of orbitals involved in creation of excited states do not interact, one can neglect these terms. So the B coefficient will be 0, and A coefficient will be only subtraction of occupied and unoccupied orbital energy. And then I'm going to flip back to previous slide. If we do have only energy differences on the main diagonal and all other elements will be 0, then as a result of solving this equation, the only available eigenstates will be energy differences between occupied and unoccupied orbitals in our original approximation of non-interacting orbitals. In case one allows Coulomb interaction, then there are two ways to take into account. So 4 indices, 1, 2, 3, 4, difference of positions in space, integration over this position in space, and then this pairs of orbitals, I, A, J, B, and here I, J, A, B in the antisymmetrized form. But computation of such integrals of interaction, Coulombic interaction with all 4 orbitals explicitly implemented is always a hard computational task. And main achievement of the designers of the TDDFT theory, TDDFT, main achievement of the designers of TDDFT theory is that this Coulombic part can be replaced by the second derivative of energy, second functional derivative of energy. And since there are different points in space, one uses this second functional derivative over density explored at point r and point r prime. So if this procedure can be practiced, then one can form these A and B coefficients and solve the form this Casida equation. How? Let me scroll back to the equation that we are focusing. So this equation gives us transition densities. Suppose we have solved, or computer this theory has been implemented, and these equations are solved. What do we get from it? What is our benefit? How can we compute observables and make relation between our computation and real life? So here I'm drawing once again these transition densities, these blocks that are off diagonal for total density, and let's look on the subtraction of the total density that is frequency dependent upon photoexcitation and density of the ground state. So it is the measure how much the total density has been perturbed by optical excitation. So if we do know this, the density matrix, the density, there is an important thing, an important chapter from quantum theory. So the first line is a standard way of finding expectation value of observable if you know wave function, or matrix element if there are several possible outcomes. Under the letter O, it can be any observable, like dipole, position, momentum, angular momentum, something more complicated. If we migrate, if we move from the language of wave function to the language of density matrix, then observable is computed, expectation value is computed as trace of product of density matrix times the operator of this observable. So with this background knowledge, we can use the transition density matrix eigenstates from the Casida equation in order to find some observables. So which observables do we need? We do need transition dipole moment, because transition dipole moment squared gives us oscillator strength, the ability of material to absorb light at given frequency. So instead of rho, we are going to use x and y, and our plan is to, well, not our, but plan of the programmers who were implementing TDDFT into programs, is to take eigen vectors of transition density matrix plug them into this protocol for finding expectation value, and instead of expectation value, one would use the operator for dipole. So the plan is to find a transition dipole and then use it for computing and reporting spectra. So here is a very oversimplified example. How does one practice this? And let me give you a little disclaimer. You can lean back and relax. This is correct information. This is important information, but it is auxiliary. So we are not going to derive these equations or change codes. So it's only for your information and interaction with colleagues in the future. So if you are close to the level of being tired, do not concentrate too much. So what I'm going to present: expectation value of transition dipole is a trace of dipole operator and transition density matrix that is found as x and y vectors in Casida equation. I'm going to look on to the very small fragment of density matrix near homo-LUMO. So on the main diagonal, it will be element for two pairs, homo to homo, LUMO to LUMO, and in the off diagonal segment, it is homo to LUMO and LUMO to homo, x and y. The dipole operator, transition dipole operator, doesn't have elements on main diagonal, but it does have non-zero elements if system performs transition from ground to excited, from homo to LUMO. So there are these D elements. So I'm going to show how this trace operation is working. So if one performs matrix multiplication in the way of row by column, so multiplication of two matrices will give another 2 by 2 matrix. So in the first element here, it will be D times row LUMO to homo. In the second element here, it will be D times LUMO to LUMO. In the third element, it will be D times row by column homo to homo. And in the last place, it will be D times homo to LUMO. Please give me little sign if you have those who have seen the symbol TR and who is happy with the mathematical procedure of trace, if you have heard about it in the past. You can either say or type. Okay. In German literature, trace is often spelled as SPUR. So trace. Now, please say or type if you never heard about this trace operation in your linear algebra class. Or if you have camera, you can just show like, no, I haven't seen.
I need to see.
Okay. So thank you. Thank you for the feedback. So the trace of a matrix is a summation of diagonal element. Yeah, thank you, Rebecca, for like if you have a matrix of 4 elements A, B, C, D, then the trace of such matrix will be summation of diagonal elements, which will be A plus D. And probably it is why it is called trace. It is not the whole matrix, but only some signature, a trace about it. So if we practice trace procedure for this multiplication of matrix, we need to take only elements that are sitting on the main diagonal. Then matrix element of the dipole can be taken out of the brackets, and inside it will be density matrix element LUMO to HOMO and density matrix element HOMO to LUMO, which will be same as D times X plus Y in our notations for Casida equation. Like if we practice Casida equation only for vicinity of the gap, it will be just summation of this elements. Then this density matrix will be reduced only to one element. So in this example, I would like to communicate the idea that if we have found transition density matrix here on the right, then it gives us an opportunity to find expectation value of the transition density dipole. Why you may ask what is new here? The new thing is that this X and Y do have indices. That this row HOMO to LUMO, they do depend on frequency of excitation. Which means, here we go. Which means that the expectation value of transition dipole will also depend on frequency. So this excited state theory has a way to show two things. First, frequencies, so at which frequencies system is able to absorb or emit quantum. And second, by finding this transition dipole element specific for given frequency, for selected frequency, it tells how intense is absorption or emission of the system at selected frequency. So it is exactly the main question of spectroscopy. It is what one needs in an experiment and what the computation can provide as an assistance to spectroscopy. Here is the same thing that we just practiced. And so from X and Y, specific for frequency, we have this perturbed density, we get transition dipole, and this transition dipole is plugged in to oscillator strength, right, through the equation that we discussed last time. And this oscillator strength has index I. So by now we do have two sets of data that come out of the Casida equation, set of frequencies and set of oscillator strength values. So by practicing these two sets of data, one can compute the absorption spectrum. In our previous considerations, I'll do it here. In our previous considerations and in the computations that you are likely doing for the project, we compute absorption spectrum by setting up oscillator strengths that depends on pair of orbitals. right? Oh, I hear someone switched on the microphone. And one is looking for transition energy is also expressed for the pair of orbitals. But if we are speaking in the excitonic picture, if we are speaking in the language of solution of transition dipoles, then this double summation, double indices are replaced with single index. So it will be energy, transition energy labeled by index I, and it will for this delta function, and it will be oscillator strength also labeled by index I, and it will be summation only over all available excited states. So what we have considered right now is what is Casida equation and how outcome of the Casida equation helps to generate absorption spectrum. So here is our old-fashioned independent orbitals spectrum, absorption spectrum, and here our excitonic spectrum computed out of Casida equation. So I think it is very much sufficient for today. Thank you very much for your dedication for the class and investment of your time. Everyone is welcome to disconnect for now. I'll stay here to answer any questions, and I look forward to seeing you tomorrow at 5 for the lab.
Okay, thank you, Dr. Kilian. Have a good day.
Thank you, Amir. Have a good day, you too.
Bye.
Bye.
Yeah, thank you. See you tomorrow.
Thank you. See you tomorrow.
See you next time. Thank you.
Thank you.
Thank you.
Thank you, Mike.
Okay, thank you.
Thank you.
Thank you, Dr. See you tomorrow.
Thank you, Rajesh. Okay, you may type your questions. You may type your questions right away, so I will prepare to answer them.
Actually, I thought I could run the optimization